we're very happy to have Pavel Putrov, who is visiting us from Caltech. And he'll be here through Wednesday, so some opportunity for discussions these days. And today he'll be telling us about his work on 02 gauge theories.
Thank you for the introduction. Thank you for the invitation to be up here. My talk is mainly divided on this paper together with Abhijit Gada and Sergey Putrov. And also, if you'll have some time at the end, I will also mention some results which are not yet published. So the plan of my talk is the following. I will start with some motivation why we want to study equals 0.2 two-dimensional supersymmetric H series. Then I will briefly review what is two-dimensional supersymmetry and some basic parts of such series which are going to make some statements afterwards. Then I will make some statement about dualities between certain series, and then I will discuss how one can use this basic duality to obtain some other statements. Let me start with integration. First, let me mention that actually very little is known about two-dimensional zero-common series. Especially on a video. Because there are some quite a few known interesting results about linear gauge sigma model and also non-linear sigma model related to heterotic amplifications. Results by different people, including Ilavian. But so far, there is almost no known fact, no non-trivial statement about the dynamics of non-abelian gauge series. So I'll work in a sense to improve this situation. Another reason to study two-dimensional zero-common series is the following. And this is the reason why, in particular, we were interested in zero-common two-dimensional series. So one can consider six-dimensional n equals 2,0 superconformal field theory, which describes a stack of n brains in M theory. This is some mysterious theory for which there is no known Lagrangian description. But what can one do? One can compactify it on a d-dimensional manifold MD with some topological twist in order to preserve some part of the supersymmetry. And this will give us some effective 6 minus d dimensional theory, which people usually denote by T of MD. So we have a class of series labeled by manifolds, and the usual philosophy tells us that if you have some statements about geometry of these manifolds, it can be translated into physics. Some statements about physics of this series. So in particular, if we consider four manifold and four of general holonomy, we can make a twisted simplification of the six-dimensional theory in a way that we preserve 0,2 supersymmetry in 2 dimensions. So this was so this problem was initiated by Gariota, who considered relation between Riemann surfaces and n equals 2 4-dimensional series. And this relation was studied in our previous paper. But in this talk I won't discuss this part. This was the integration part. Now let me briefly review some facts about the dimensional 0,2 series, which I will need later to make some statements. So, 0,2 symmetry has 2 supercharges. Plus bar. So these are 2 spinors of positive chirality, which means that we consider U1 rotations in Euclidean space-time. They both have charges plus 1/2. And as usual, when we have extended supersymmetry, there is U1 arc symmetry, with respect to which these charges have opposite charges. And these 2 supercharges obey the following relation. The anticommutator gives twice P plus, where P plus is a component of the momentum along the right moving direction of the light cone. Or if we are in Euclidean space-time, this is the same as the zeroth component of the anti-holomorphic Virasor algebra. So this series can be usually formulated in superspace, which consists of 2 space-time coordinates along the direction of the light cone, and also 2 Bernoulli particles. So general 0,2 theory can contain the following multiplets. Here there is a chiral multiplet for which superfield representation reads as follows. So it contains usual bosonic field and also fermion of right chirality. Then there is a Fermi multiplet for which superfield reads as follows. The lowest component is the left oriented terminal. And there's an auxiliary field. And here we have some arbitrary holomorphic function of chiral multiplets in our theory. And then there is a vector multiplet superfield following. So we have minus component of the usual H field. We also have left fermion. And these are the So let me know, so for example, if theory has just some left moving fermions, it can be in a way, in a trivial way, it has 0,2 supersymmetry because we don't have any supersymmetry in the left moving spectra.
So why isn't the P plus S0 plus S0 bar? Maybe it's a trivial question, but I thought the Hamiltonian is always M0 plus S0 bar.
This is a Hamiltonian only in one of the light direction.
Okay, so don't you need to add the other component too? Or not? Maybe it's a trivial question.
No, this is just, I mean, this is not a Hamiltonian.
Oh,
I mean, this is only becomes a Hamiltonian if you do light quantization, but in principle, this is not a Hamiltonian.
Oh, I thought
This is
the energy. Well,
P plus is a momentum is a component of the momentum in the light in one of the light quantum direction.
Yeah. So the zero component is the energy. Oh.
It's a peculiarity of two-dimensional theories. You can have this PQ supersymmetry
Yeah.
with left and right supercharges closing onto.
I mean, in general, we have some supersymmetry relation looks like some anti-accumulator of supercharges give some components of the momentum.
Right.
And this is just a particular choice of.
So what is A minus?
A minus is just the component of the vector field, of the gauge vector field along the left moving direction of the light.
So any kind of current, right? Plus or minus?
And this is minus.
Oh, minus.
Minus one.
Yeah.
That's the question. So in locally for fields this is just plus in Minkowski space, and this is D bar. Euclidean space. Ask questions. Is it okay to write here, or it's better to? So what kind of interaction can we have in general for zero quantum gauge series? First, there's a usual interaction between vector multiplets and matter, which can be chiral or Fermi multiplets. The interaction which is given by just gauging a certain symmetry. Then there can be interaction between Fermi multiplets and chiral multiplets figured by introducing this arbitrary holomorphic function of chiral multiplets here. And then one can also add the following superpotential terms in Lagrangian. The following form. We have the plus Fermi multiplets times some holomorphic function of chiral multiplets. And we also have to pick the components. This is some superfield for which we can pick out the components which picked up by this relation. And one can also show that these two interactions are interchangeable, they're equivalent. We can either DC or with J, this is equivalent.
If you only have one or the other.
Yes, well, no, I think if they're both, there are some additional relations that they must
Yeah.
satisfy.
Yeah, that's right.
But in the example that we should consider, we will only have this.
So what constraints is that you can have just one or the other?
So, I mean, okay, the constraint. So if you have some additional field, if you have some bunch of Fermi multiplets which are labeled by some index A, so for each of these Fermi multiplets, we will have this function EA, and we also have some function A, and this should satisfy the following condition. Otherwise, the supersymmetry won't be preserved.
Oh, I see.
Another important feature of two-dimensional zero-commutative series is that in general they have anomalies of symmetries. So suppose we have some symmetry generators GA, then one can consider divergence of the corresponding current, and it turns out that at one loop it's not zero, and divergence is given by the following expression. So it's proportional to the corresponding field strengths. Some coefficients, which is usually called anomaly coefficients. For which there is the following expression: trace over Fermi fields of gamma 3, which is usual chirality matrix, plus or minus 1, depending on the left or right moving terminal. The product of the following generators, these symmetry generators. So if we want to gauge some symmetry, it should be non-anomalous. And this usually puts some non-trivial constraints on the parameters of our series. So for example, if we want to gauge some U1 symmetry, the anomaly coefficient, so there's only one generator, the anomaly coefficient is given by, which we denote by Q, the anomaly coefficient is given by this, and this reduces to the following expression. So we have a sum over all chiral multiplets Phi of their charges squared minus the sum over all Qi squared, where Qi's are charges of Fermi multiplets. So here we have plus because gamma 3 is equal to plus for fermions higher multiplets, and here we have minus because gamma 3 is equal to minus for left moving fermions here. Any questions?
Yeah, but does it come from what you're writing, and why is it an anomaly? I mean,
I mean, this is some one loop configuration.
it's a one contribution,
it's-
so where does this expression come from? How do you calculate it?
I mean, this, I mean, either one can calculate in one loop diagrams, or you can also consider explicitly how the metric, how the measure in the path integral changes. This is basically the factor, the coefficient. This is the factor which appears if you make a symmetry transformation as a measure of the path integral.
But what does it mean in terms of physics? Let's say, does it mean that, usually we consider, let's say, hexagon cancellation, that Z boson doesn't decay into particles, but in your case, would it mean that E particle would decay into 5 particles? because of this anomaly cancellation. But would it mean in terms of physics, let's say if you draw the Feynman diagram, V decaying to 2 pi, would it be non-zero?
Yeah, I think. Yeah, yes. Yeah, because in principle this diagram is just like this. Well, anyway, it's not.
It's not the main topic, right?
Yes, it's. The other thing which I will need later is a quantity which is called heterogeneous.
Excuse me. Can I ask a last question about the anomalies? Does it form a Katsuri algebra? I mean, do you get them in the second order code, or if you take the current algebra, symmetric generators?
Yeah.
Because the notation looks like that.
I mean, basically, what if you have some flavor symmetry can be anomalies, and basically the coefficient, the anomaly coefficient, yes. In the superconformal, if you consider theory in deep IR, we have some superconformal theory, and this means that this flavor symmetry becomes Kac-Moody. The asymmetric algebra becomes Kac-Moody algebra, and this would be the level of this algebra. So we have, for example, SUN, and the anomaly coefficient here is some K. So this means that in IR we have SUN at level K. So the epic genus is basically the same as Witten index, gradual quantization. Function of Q and some other parameters which usually called Fugasity's AE. Its default is false. The trace of the Hilbert space of a series put it on a circle. -1 to the Fermi number to the L0 to the L0 bar. And we also can have point insertion, the product of IE to the Fi, where Fi are the ungenerators of wave symmetries. It's usually one does for Witten index, one can show that this trace actually reduces to the trace over a subset with zero eigenvalue of L0 bar, because you have supersymmetry in the right moving sector. And finally get some homomorphic function Q and AI. So the index is, one reason the index is useful is because it's a nice indicator of supersymmetry breaking. So if for some theory happens that the index is equal to 0, this is an indicator of SUSY breaking. because unless there are some accidental constellations here, this means that basically this space is empty, so there's no supersymmetric ground state. So this elliptic genus is a nice quality, it doesn't depend on any continuous deformation of the theory, and this fact can be used to calculate it exactly for series, for gauge series, satisfying some mild assumptions. Let me briefly mention how one calculates the index. So I will give, what I represent is not a calculation of the index, but is just a prescription how to write the answer for the index. First, step one is multiply the point contribution from all multiplets. So there's a chiral multiplet. For each chiral multiplet, suppose it has some arc charge R. We should insert the factor. Okay, sorry, I forgot make certain definitions. First, I will use the following relation for the Hammer symbol, symmetric product, and also multiplicative theta function defined in the following way. So the contribution from every chiral multiplet.
Pavel, sorry, I just can't read that second term. That's Q over X comma Q. Is that right?
Yes.
Okay.
So this expression. Oh,
yeah.
Sorry.
Okay.
Theta function, we first insert Q to the R over 2, where R is R charge, then insert the product of the fugacities for flavor symmetries, where this power is equal to charges of this multiplet. And we also should introduce, at step 1, we should also introduce fugacities for gauge symmetry, if you have any. And QIs are charges of the chiral multiplets with respect to the cartons of the symmetry associated with the fugacities. For Fermi multiplets, we have almost the same expression, but we have theta function in numerator. And for vector multiplet, suppose you have gauge symmetry. This means that we have m gauge fugacities Zj have the following contribution.
Sorry, I'm still confused. So theta is a function of one of just x?
Yes. Okay.
Uh,
Maybe some. Usually
It's a function of
Usually people write it like this.
Okay.
But just to make it short, I write it just like this.
Okay.
And we always have
Q is always around.
Yeah.
Yeah.
Q is the
okay,
second
good.
argument. And then step 2 is integrate over gauge. This is so the final expression for the index has Q and Pavel fugacities given by the integral over all the J of the expression which we obtained in step 1, which is some function of Q, A, and Z. So the integral should be in front of a certain contour, which I won't discuss what is the exact description. Any questions?
What is fugacities? Gauge fugacities? What is that?
Okay, so basically, suppose we consider a simple example. If you have U1 gauge symmetry, this means we have only one carton generator, and we introduce one fugacity with denoted by Q. And we can introduce, for each carton, we introduce some fugacity. So in which case, in this case, this will be only one variable. And so for chiral multiplet, if chiral multiplet has charge Q, we just insert Z to the Q. So if you have, for example, a chiral multiplet suppose we have UM gauge symmetry. So that means we have M carton elements. For each carton element we have the I. And for example, chiral multiplet in fundamental representation, we should write. So there are n chiral multiplets which form fundamental representation. So there will be product of I questions? So now let me discuss technical of basic duality. So first to define a theory which has this duality, let me use quiver notation. So it's usually we have some nodes corresponding to symmetries. So squares are nodes corresponding to flavor symmetries. Circles correspond to gauge groups. And then there's the lines. So in our case, we can have matter of two different types, either as chiral splits or as spiral splits. So with solid lines between two nodes, they may be circular or square. We denote a chiral split in the fundamental representation, which means it's fundamental with respect to this group and anti-fundamental with respect to this group. And by dashed lines, we will denote chiral splits in the fundamental representation. What we want to consider is some UNC gauge theory which has three flavor symmetries: UN1, UN2, and UN3. Which will be represented by the following field diagram using the rules which I just defined. UNC gauge symmetry is denoted by this square circular node. And we have three square nodes corresponding to these three flavor symmetries. And we have matter represented by lines. This means that we have some chiral multiplets in the fundamental representation, fundamental respect to gauge group, and anti-fundamental respect to UN1. And we have some chiral multiplets which we denote by P. And we have some chiral multiplets gamma. And we also have some chiral multiplets psi. And we also want to consider the following superpotential term. Which gives interaction between these three fields forming a triangle. General choice of parameters, this UNC theory is actually anomalous, and in order to have non-anomalous gauge symmetry, have to pick up NC equal to the following quantity, some linear combination of ranks of flavor groups. But this is actually not enough, because this will contain only a SU part of anomaly. of this group, and there is also U1 part of this group. And in order to cancel this U1 anomaly, one has to add additional meta content, which is quite simple. So we want to add 2 Fermi multiplets. That is denoted them by omega 1 and omega 2. And this Fermi multiplets will only be charged with respect to U1 parts of all these 4 groups. So you consider U1 part of the gauge group, which one usually denotes by determinant. These 2 fermions have the same charge, and we have the following charges with respect to U1 parts of flavor groups. Yes.
What does diagram represent?
Sorry?
What does this diagram represent?
The charges, we have 2 ferromultiplets. This is the charges with respect to this.
No, I'm about this diagram. What is that?
This is what I explained the rules on that part of the blackboard. This basically represents the matter of the so all nodes represent flavor of gauge symmetries, and the lines between represents matter.
So what I meant, so it's not like a G factor of whatever your Fermi field. It has nothing to do with G factor.
So any other questions about what is this theory I want to consider?
And then superpotential is the most general you can write with these symmetries.
Yes.
Yeah.
And in general, I can say this is more or less the basic trivial gauge theory, non-billion gauge theory, which you can invent with having non-anomalous gauge. So let me define the following variables. This is just a notation to conserve space. So n is just the following sum of all these 3 arcs over 2, and I will also want to define small n i's. All these new numbers are just the linear combination of flavor ranks. So then our theory on the like this. And what we want to propose? We want to propose the duality between this theory and the following theory. What we did, we basically just cyclically omitted these flavor ranks and replace it N3 by N2. So if it indeed happens to be a duality, then one can do the same operation on this theory, and this will give us the following diagram. Just repeat the procedure. one does this once again, we arrive at the original theory. So it basically means that we have what we can call a triality. This is a
In all
relation-
of these cases, the anomalies are cancelled.
Yes. Yes. As you actually see here, N3 is some function of these numbers with some preference of N3, and this is just here we have N2 and here we have small. So how one does argue that this is indeed the case that there is such a duality? So what one can do is do the matching of the indices of this series. Show that the index of this series is the same as the index of this series.
But they are talking about a strong weak duality, are you? Well, one is strong, but one is weak.
I mean, in some sense it is, but I mean, I wouldn't call it just the extra.
It just turns out you calculate observables and the same things go on.
Yes.
For everyone or something.
Yeah, and first let me mention this is duality because we actually will match index. So index only counts massless modes. So this is duality between infrared fixed points of this series. And in a sense, this is also similar to Zapek duality in 4 dimensions. But the duality is just a duality, not in the series. So index matching is actually quite powerful because index contains a lot of information. From index matching actually follows as a consequence that the central charges of this series match. And also flavor anomalies match. Questions?
I suppose that one could also test whether the discrete global symmetries these models match. I don't know, so I guess the question is, are there non-trivial discrete global symmetries left over here?
Yes, I think there are some Z2 symmetry.
But that's all, it's pretty small.
Yes. So this is some non-trivial statement on its own, but one can use it to deduce some additional statements about this series. So first one can show that the index of the series is 0. This means that sum of this small n etas is less or equal to 0. So this basically means that in one of the frames the rank is formally negative. But this basically means that we have some trivial symmetry trivial theory in infrared. The index is equal to 0.
Like you calculated it or what? Or why is it 0? Or it's trivial at 0?
No, it's some not trivial statement.
Oh, you calculated it.
Yeah, you can show that the index. I mean, just start with one theory and yes, start with a certain theory, not using duality. You can show the statement.
Oh,
I'm just saying what formally it means if one considers duality, if one considers duality. And this means that we have unbroken SUSY. So when the index is non-zero, which also means this simply is unbroken. All MRs are greater than 0, which can be rewritten using these relations as some triangle inequalities for flavor rank. It basically means that the flavor ranks can form a triangle. So this can be, so this region can be depicted in the following way. So let's consider the following diagram, which represents the space of all this series. So it can be nicely depicted as the interior of a equilateral triangle. So that if you pick a point, the distances of this point to all edges are equal to the n1 over n, n2 over n, and n3 over n. So we use the fact that there's no fact that the sum of all these three lengths is constant, and we see that by the definition of n, this is indeed the case. We can always represent a series by points in this equilateral triangle. So, but if we first consider these inequalities, this cuts out a certain subspace, a smaller equilateral triangle, where we have unbroken SUSY. And one can also show that the boundaries of this triangle are places where we have theory which is dual to a certain free theory.
I'm sorry, I'm missing. What? Is there a way to see that? Why are the edges?
I mean, one can use a triality to show that the after making this duality, we arrive at just so. For example, if actually if this n1 is equal to this small n3, and it will be 0. So we are left. We are left only this Fermat multiplet, which is just free. Show also the following example of how can we use duality. So consider the case where all flavor ranks are equal to 2, which means that x equals to 1. So this actually means that all these three series are equivalent. I mean, they're basically the same, we just moved flavor groups. In each frame, and let us also forget about U1 parts of flavor symmetries. So in each frame, our theory will look as follows. So we have U1 gauge theory, and we have 3 SU2 flavor symmetries. But we also know that we have those additional extra 2 fermions which were charged only with respect to one part of the gauge symmetry. But in our case, the the gauge symmetry is equal to its U1 part. So this is omega multiplets is actually one can say that they are actually in fundamental representation with respect to this one. This is the same thing. And since there are two of them, there is also SU2 symmetry which rotates them. Because we can forget about all U1 charges of Fourier symmetries. Here we have some two ferromultiplets psi. And now I can see that in this picture, this ferromultiplet is actually indistinguishable. And this means that it actually should be enhancement of Fourier symmetry to SU4. In this case, there is no difference between psi multiplets and 31 here. And but one can
Sorry, but doesn't the superpotential predict the symmetry?
No, there's no superpotential, only involves this guys.
Ah, right, it's the, got it, okay, uh-huh.
Superpotential is straight to this term.
It's just A1, P5, okay, right. Uh-huh.
And then one can use duality, which basically permutes these three SU2s. And that means that this SU2 can be also combined with this SU2 and enhanced to SU4, and also combined with this SU2 and enhanced to SU4. And one can deduce that it should be that the flavor symmetry is actually E6. So this can be seen if you consider extended diagram of E6. It looks like this. So we have, you can say that these external three nodes correspond to these three SU2s, and this node corresponds to this SU2. And there are three different ways to enhance these two pairs to SU4. So I'm almost out of time. Let me just mention briefly what some other things we can do. So one can use this as a basic building block to consider some more complicated theories. So, for example, one can consider two copies of this theory, build something like this. So basically, consider a flavor group for this first block as a gauge group for the second block, and vice versa. And then we can use this triality which acts on these basic building blocks to play with this stuff, and one can make different statements. For example, one can show that this theory is equivalent to this. Where he fixes four nodes. And one can see more complicated stuff and build some rules, nice rules to build more complicated pairs. But we don't have time to talk about this. So I think I will stop here if you have some questions.
Thank you. So, questions for Pavel?
Do the scalar multiplets form some interesting target space geometry?
Yeah. I mean, one can rewrite this theory as some nonlinear sigma model. It's basically some combination of tangent and normal bundle to Grassmannian. This answers the question. Should I explain it?
Yeah, it was just, so the number of scalars was it n1 or?
I mean, it's n1 times n3. the impact on the metal of this scalars of twice. And the number of these scalars is n2 times.
It's also times little n3, right?
Oh, so I mean, this is a regional number, but if you use, I mean, if you want to do this usual reduction with respect to, like Taylor reduction with respect to gauge group, we will get something like, we will get the equivalency model description, the target spaces, Rachmanian of 3 planes, and 3 planes inside in one dimensional space.
Just I have a simple question, just back to your triangle. So whatever the triality works inside of the shaded triangle, right? Because there you have unbroken solutions.
Yes.
Right. So what happens to your wonderful triality in 3 other triangles?
I mean, if you hear, I mean, basically the conjecture that this symmetry, this sphere doesn't have supersymmetric vacuum. It's supersymmetric vacuum. I mean, we don't say.
So this triality breaks down, right?
Yes, I mean, we can say anything. Yeah.
Not even to say that whatever the non-SUSY theory is in the upper triangle is related to one in the.
It's equally broken.
You know that you can't say anything about it, but maybe it's still the same, or
It's equally bad, right?
or equally good, depending on your taste.
Or can you make a transition?
I mean,
No, probably not.
we don't have any.
Control.
I mean, we don't have any. Yeah, I mean, we don't have any massive space at all. I mean, there's nothing to speak of. Because we don't say even inside the fragment, we don't say that there is a triality between also between massive spectrum. We don't say this.
Other questions? All right, no,